So I'd like to try a few problems here that focus on vectors, specifically the sum of vectors and the dot product between vectors. So let's say that I have two vectors, vector u with these components, vector v with these components. Suppose the goal was to find this and this. This is the dot product between two vectors, denoted by a dot symbol. It looks like multiplication. We call it the dot product. This is the sum of two vectors. So I won't get into the theory behind this. I won't explain what's going on behind the scenes. I'm just gonna show you how to get the right answer. So for u dot v, here's what I do. So u dot v is a dot product. So what I do is I multiply this x with this x. And then I go addition. And then I multiply this y with this y. And then we go addition. And then we multiply this z with this z. And then we compute this here, so we have negative 82. So if I take these two vectors and if I find their dot product, the dot product is negative 82. So again, when they ask you to find a dot product, the result is more than likely just going to be a number. The dot product between two vectors is a number. What this means, what this does, the applications thereof, we can do that a different time. For now, boom, that's how you find the dot product between two vectors. Now, the sum. So, if you want to add two vectors, you have to add them component-wise. For instance, 5 and negative 7. Add them. What is the sum? Negative 2. That and that. Add them, positive 2. This and this. Add them, negative 7. Done. So, that is how you find the dot product and the sum of two given vectors. And so now let's take these ideas to the next level. So here we're given three vectors, u, v, and w, and they want us to compare a couple of items. They want us to compare the dot product between u and this sum with the sum of this dot product with this dot product. So first things first, let's focus on this here. So u dot v plus w. By substitution, I will drag and drop all of these items where they belong. So let's see. U is literally right there, right? Because that's what U is. The dot is right there. That parenthesis is right here. V, which is that, is right there. Addition, addition, and W, which is that, is right here. Close the door, close the door. So now, let's see what this becomes. I am going to work with PEMDAS. I'm looking only here. If I want to add two vectors, I add them component-wise. So let's see. That stayed the same. The dot is still there, waiting for us to apply it. I added the x's, boom, the y's, boom, and the z's right there. And so now let's actually do the dot product. And then recall for dot product, you multiply the x's, multiply the y's, multiply the z's, and add them all together. And I believe it should be 9 if you perform all of this arithmetic. So that is the value of this. Now let's focus on this stuff here. So by substitution, let's replace these vectors with their components. So let's see. The dot product here, so we multiply x's, multiply y's, multiply z's, and add them together. And let's see what we get here. And as it turns out, we actually get back the same value. So the reason that they had us do this exercise, comparing this with this, is probably to get us to believe that this is in fact the same as that. It's kind of like the distributive property. Remember that? How that you can, in a sense, distribute the u. So it'd be u dot v there, and in addition, u dot w. So it kind of behaves and mimics the distributive property. Now, before I let you go, I did omit the little symbol for a vector, which I believe is that. Sometimes they do it like this. I skipped that just for the sake of time. Also, note that parentheses versus the vector notation, right? When you see this symbol, that is the symbol that we use for the components of a vector, as opposed to parentheses, which are, a different application. I hope this video was helpful, and go off and try your problem and let me know how it goes.